Quantum mechanics presents a physical contradiction. We model a particle as a smooth, continuous wave packet spreading out over space, and yet, at the moment of detection, that wave arrives as a single, localized point of impact. The Schrödinger equation governs the evolution of that wave function, advancing it through time with smooth, absolute determinism. Laboratory experiments, however, never observe this spreading wave directly. We only ever detect discrete, indivisible particles landing at specific coordinates on a detector screen. The wave function carries a probability amplitude, a mathematical distribution of likelihoods that determines the statistical odds of finding a particle at any given location. Quantum measurement acts as an active physical projection. It compels a probabilistic system to commit to a definite state, a transition defined by a strict new set of rules. To analyze these rules, we use the simplest possible quantum system, the two-level system, or qubit. The qubit lives in a two-dimensional complex vector space called a Hilbert space, written as C2. We define this system using two computational basis states, represented as ket0 and ket1. Any normalized state of the qubit can be constructed as a superposition of these two basis states, alpha 0 plus beta 1. This superposition exists as a pair of complex numbers, containing the complete mathematical blueprint for the system's behavior during a physical measurement. The measurement postulate serves as the formal bridge between the abstract mathematics of the wave function and the physical reality of a laboratory result. This process occurs in three stages. First, a superposition branches toward two outcomes, following the Born rule probabilities. Second, measurement yields a specific eigenvalue. Finally, the system collapses into that pure eigenstate. Remeasuring this new state instantly yields the same result with total certainty. We can ground these abstract rules in the physical laboratory by tracking particle spin through the magnetic fields of a Stern-Gerlach apparatus. In this first configuration, an initial z-axis measurement collapses a particle beam. Blocking the lower path isolates a strictly z-up beam. Entering a second identical z-axis apparatus, it remains on a single path. With no further splitting, the probability of remaining z-up is exactly 1. This physical result matches the third stage of the postulate. A collapsed state is stable when it is remeasured in the same basis. Stability depends entirely on the axis of measurement. If we rotate our apparatus to measure an incompatible property, like spin along the x-axis, the state changes again. If we pass our known z-up beam through an x-axis apparatus, the beam splits into two equal parts. A particle in a definite z eigenstate is actually an equal superposition of x-up and x-down. Viewed from the x basis, the original z-state certainty entirely disappears. Measuring an incompatible property forces a known definite state back into a probabilistic superposition. We can now execute a critical test of quantum information. Does a system retain its original z-state if we interrupt it with an x measurement? We prepare a z-up state, pass it through an x measurement, block half that beam, and then measure the z-axis a second time. The final z measurement results in a 50-50 split. This outcome contradicts the perfect stability we saw when the x measurement was absent. The intermediate x measurement actively destroyed the system's prior z-state information. Observing a quantum system is an irreversible act. Extracting one type of information erases another. This physical erasure is represented mathematically by the Pauli matrices. When we calculate the commutator for x and z spin, the result does not equal 0. Non-commuting observables make it mathematically and physically impossible for a system to maintain definite values for both properties simultaneously. This randomness is an inherent property of the quantum state itself, persisting regardless of the precision of our measurement apparatus. Measurement creates the reality it records. Particles only assume definite properties at the moment of observation. While the wave function provides the probabilities, measurement acts as a strict destructive projection. If these rules of superposition and collapse apply to a single qubit, what happens when two separate qubits share a single wave function? Scaling these measurement rules to multi-particle systems leads to entanglement, the next consequence of the quantum world.